All right, guys, so here's my shot at redemption. So as we looked at, this was the first one. We have the limit as sine of x over x approaches 0. So we said that, okay, typically we like to break this up and say, okay, the limit of the first times the limit of the second. But the issue with that is when we take the limit or plug in sine of x is 0, and then 1 over x is infinity. We can't do 0 times infinity, so then that's when we start to try to apply some knowledge. So the missing information that we need to start this off is actually, part of it is up here. So we know that when we're working with sine of x, they told us up here that sine of x has to be less than or equal to x. So here's our upper bound. So we're going to start from here and use that knowledge. So we have sine of x has to be less than or equal to x. Okay, so here's where we start to manipulate algebraically. So our goal is to get sine of x over x. So in order to do that, we need to take a moment and divide both sides by x. Okay. So you might be saying to yourself, but Mr. Kravakis, this is a squeeze theorem. We need something below a lower bound and an upper bound. Well, if we look at our second piece of information here, we are looking at the fact that sine of x over x has to be greater than cosine. So here is our lower bound. The reason why we can use this information is because we are evaluating our limit as it approaches 0, and we do know that this is true when our x is between negative pi over 2 and pi over 2. They tell us this up here. All right, so now that we know that sine of x over x has to be greater than or equal to cosine, we now have this squeeze going on. So let's clean this up a little bit. We have cosine of x as the lower bound. Sine of x is what we are trying to figure out the limit of. And then our upper bound actually simplifies to 1. Okay. We are now done with as much algebra pre-calculus knowledge as we can apply. So now this is where we transition to our limits. So I'm going to take the limit of all the pieces. The limit as x approaches 0 of cosine of x, if we plug in 0, again, we plug in first, right? We plug in 0, cosine of 0 is 1. Then the middle part is the limit that we are trying to figure out. And then the limit of a constant, no matter what we're approaching, the limit of a constant is always the constant. So we have now squeezed this limit in between ones. So this one we will explore again once we have talked about this idea of a derivative. Typically, you are able to solve this one utilizing derivatives versus utilizing Squeeze theorem, which reiterates my statement of Squeeze theorem is nice to know, but not strongly aligned with a majority of your questions on the AP test. So for this one, the limit is 1. So now for this one, we actually needed to figure out the first one before we did this one, which is why I ended up confusing myself in this one too. So we needed to do a little bit of manipulation with this one first, and then you're going to see how the other one that I just worked through shows up. So we know that we have this idea of a conjugate pair for when we're working through trigonometric identities. Pythagorean theorem is one that shows up most of the time. So we're going to multiply this one by the top and the bottom. by 1 plus cosine of x, so that when we end up foiling everything out, we end up with 1 minus cosine on the top, or sorry, cosine squared. And then on the bottom, we just leave the x and we have 1 plus cosine x on the bottom. So as you guys know from pre-calculus, you are looking at 1 minus cosine can change into sine squared. And then on the bottom, again, we have x, 1 plus cosine x. Okay, where do we go from here? Here's where we can go back to the idea of separating our limits, thinking about having the limit of a product. We can create the product of two limits. What does that look like? How would we break this up? Well, we can look at the limit as x approaches 0 of sine of x over x. That is one of these and x. But we have technically sine squared, which means we have two sines being multiplied in the numerator. So that allows us to then multiply by the limit as x approaches 0 of sine of x over 1 plus cosine of x, which comes from the other one of these and this. One of these should look familiar. The yellow one that I just underlined is the one that we just proved. We just proved that this limit is equal to 1. Again, I can drop the limit notation because I have taken the limit. The second one that has highlighted with green, we can plug in, because when we plug in 0, we get sine of 0 over 1 plus cosine of 0. So when we evaluate sine at 0, we end up getting 0. And when we end up evaluating cosine at 0, we get 1. So this ends up being 1 times 0 over 2, which translates to 1 times 0, which is just 0. So when you are working with the limit as x approaches 0 of 1 minus cosine of x over x, you are allowed to just say that it is equal to 0. This one can also be solved by using what we're going to learn called a derivative. But for now, this is how we would work through this utilizing the squeeze theorem.